Good morning, good afternoon, good evening, depending on your time zone. Uh, Many of you know me already. I'm David Cantor, one of the founders of MLCommons and head of MLPerf. I want to thank you all for taking the time to join us for the embargoed briefing on MLPerf Training version 5.1. So just to be clear about that embargoed part, this is under embargo until the 12th at 8 a.m. Pacific time. This meeting is being recorded, so it will be available for your consumption later. And then with me, I have the fantastic team that works on MLPerf training, Alejandro Caruso, Shreya and Paul, and Shreya and Paul will be presenting alongside me. And then we have, I believe, our 20 submitting organizations represented here, and I'll get to talk about them in a little bit. So, for those of you who are familiar, we usually, for our friends in the press and analyst community, we have a wide variety of briefing materials that we share. They're documented in this slide. They're distributed through Google Drive and then the results via email. One of the things I want to point out is we actually have two supplemental blogs on our new benchmark. Those are also public as well. And I think we got them out about a week ago. And then this video, once it's recorded and cleaned up, will be in the Google Drive as well. Next slide, please. So this is our rough agenda. We're part of the way through the overview, and then I'll be passing it to Paul and then to Shreya. So if we want to click through onto the next slide. Oh, and of course, as always, we'll have Q&A with the submitters at the end. So I hope you all are prepared with your questions for our submitters. MLCommons is a trusted, open governance nonprofit organization. We bring together industry and academia. We have over 125 members spanning the globe, and we work on many projects that are oriented around how we make AI better for everyone. MLPerf is, of course, the one that we're all here to discuss today. We have over 90,000 performance results across six, actually possibly seven benchmark suites now. Our benchmark results are reproducible. They're used by buyers and sellers all across the world to help measure performance in an industry standard way. We also have some benchmarks that are looking at other areas of ML. I want to call out our friends in the AI risk benchmarking world. So we have efforts there that help to start quantifying risk and reliability of AI. That's a new effort for us. And then, of course, there's a lot of work we do in the data area, looking at data formats, data sets, and other things that will help to empower AI to move forward and bring the magic of AI into the hands of more people. Next slide, please. So just as a baseline to talk about some of the main goals of MLPerf, one of the ones that I talked about earlier is, we are an open, trusted, and neutral organization. We create a fair and level playing field for everyone. That is one of the key principles and goals behind MLPerf. It's part of what makes MLPerf so complicated, is ensuring that level playing field for everyone, from the smallest player up to the largest players. Our benchmarks are chosen to be representative of what is commercially relevant. We know that people are going to put a lot of time into their MLPerf submissions, and we want that to benefit the whole industry, so that not only are we bringing customers and vendors together to help understand what is a good solution, but to make those solutions better. We want everything to be fair, transparent, and reproducible, because that is ultimately about trust, which underlies all of what we do. And, again, the goal is how do we serve the whole community, not just people who make silicon, not just people who make systems, not just software vendors, not just model providers, but, truly everyone, from folks in academia who are going to find the techniques that bring us performance in the next generation, to the folks who are trying to decide what to buy today. And we all have to do this in an affordable way. Benchmarking is critically important, but we want to make sure that we keep in focus that this is benchmarking in service to the broader community. Next slide, please. Uh, One of the delightful things about ML is that it is a full system problem. It is a full stack problem. You oftentimes see people talking about how they're optimizing at all levels of the stack, not just any one of these. And I really want to emphasize that that is the case. And that is both great because it gives us a lot of tools to help improve performance and energy efficiency. But it also makes benchmarking challenging, right? We can see improvements in performance from everything at the lowest level of the silicon or the packaging to new memory technologies to improvements in software to more advanced numerical formats that reduce the memory usage and allow you to use more flops, right? To scale up to bigger and better systems, to distribute work in different ways. So there's a huge amount of complexity that goes into making ML work. And that is behind each benchmark submission. But the advantage is that as we look at how we drive forward with more performance, this gives us a lot more levers to pull on. Next slide, please. So the MLPerf training benchmark is developed by one of our working groups. Again, open and neutral fair governance. Shreya and Paul are the working group chairs. And this time we had 20 organizations submitting to MLPerf training. For those who want more details about the construction of the benchmark suite, the paper here is the original MLPerf training paper that you can go and read about. Next slide, please. So just as a reminder, the goal of MLPerf training is to measure how fast you can train a model to a target quality metric, right? And this is actually something that's critically important. Before MLPerf training, there were lots of people who talked about the speed of training, but it often wasn't coupled to quality. Right. And if you've ever seen The Simpsons, I think there's this one episode where someone says, well, there's three ways to do things. There's the right way, the wrong way, and my way. Well, and then the question is, what's your way? It's the wrong way, but faster. And, in reality, you don't get points for the wrong answer, right? If you cannot converge to the target accuracy, you're not providing a valid solution. And that is, one of the critical elements here. We also have optional power measurement that looks at the power consumed by the compute nodes and the interconnect as well. Although in this round, we did not get any power submissions. It's actually considerably more complicated to do. Next slide. Now, one of the things that is really rewarding about getting to work on MLPerf is that it both acts as a guidepost for the industry and as a barometer on progress. And this is a chart that we've trotted out pretty consistently that looks at sort of the progress you would expect from, Moore's law, right? Oftentimes the pace of the overall semiconductor industry. And then we get to look at how we're doing relative to that. And the great thing is that we still see lots and lots of progress significantly faster than Moore's Law. In particular, we're seeing that with our latest benchmarks, right? And some of this reflects overall trends in the industry, right? There's a lot of acceleration going on. There's a very rapid release of new models. But it does tend to be a bit more concentrated in the generative AI space. That's a very clear theme that we've seen through MLPerf inference, MLPerf training. There's just a tremendous amount of focus on generative AI. And so it's only natural that our latest benchmarks, which do focus in generative AI, are the ones seeing the greatest performance advantages, well outstripping what you would expect from pure improvements in the underlying silicon technology. So, that's great. We're getting more capabilities in the hands of more people. Next slide. So again, this time we got over 200 performance results. I'm absolutely thrilled. We've got 20 submitting organizations. All of the submissions were in the closed and available category. I'd like to, in particular, congratulate our three newest submitters who this is their first time submitting. Our friends at DataCrunch, WeWin, and the University of Florida. And I'm going to call out the University of Florida because they're a little bit different than some of our other submitters. This is one of the first times that we've had an end customer submit. And so that's really gratifying to see. In a lot of cases, it is a tremendous amount of work. And not only did they submit, I believe they submitted to all of the benchmarks. So it's really great to see bringing sort of all parts of the supply chain under the roof at MLPerf Training. And that is in no way to take away from any of our other friends and colleagues. As I say, submitting to MLPerf is like running a marathon. It's a very impressive thing to accomplish no matter what. And just big kudos to all of the teams involved in making this happen, especially those who are doing it for the first time. It's a great barometer on the capabilities of your organization. Next slide, please. As I said, we had all of our results in the closed division, which requires that the model that you are training be mathematically equivalent to our reference model. The open division, there's more room for innovation, but all of these submissions were on available systems. That means you could go out and purchase it, right? Whether it's in the cloud or on-prem, in the closed division. So next slide, please. And so with that, I am going to turn it over to Paul Baumstark. He is our newest MLPerf working group co-chair. He recently took over, and so this is his first time. Big kudos to him on stepping up for this one into the hot seat. So thank you, Paul.
Great. Yeah, thanks for the intro, David. And it's great to be here with you all this morning or evening, whatever your time zone. Just introduce myself briefly. I'm a software engineering manager at Meta working on the co-design team. So what we do is we develop hardware and software for our next generation AI models working at Meta. So we work on internal chips that we've developed like Artemis and Athena, which were published. And we also work with vendors in making sure that our models are going to perform well on the latest NVIDIA AMD type chips. And I just want to thank Shreya and the outgoing Meta co-chair Hiwat Kasa for ramping me up this time. Cool. So in the so talking about what's new in Training V 5.1, there's two benchmarks we're going to go into more detail on. So for the two new benchmarks we have is an LLM, Llama 3.18b, and also a text-to-image model, Flux.1. Also, some other highlights from this round. So we had a bunch of new processors making their debut. So the NVIDIA Blackwell Ultra, we have the GB300 and B300 results for the first time. I believe we had the B200 and GB200 results last time in 5.0. And we also have the AMD Instinct MI350X and 355X. Plus, there's also an NVIDIA RTX Pro 6000. And on the CPU side, there were a couple of Intel Xeon processors that were making their debuts, which I think were coupled with some of the B300 chips. We didn't have any new power results this time from last time, and we didn't have any models moving from preview to available, so it was all strictly new accelerators. Next slide, please. Great. So this reviews the benchmarks that we have working. We have these 7 benchmarks detailed now. The tasks are the same as 5.0. So we still have recommendation tasks, LLM pre-training, LLM fine-tuning, object detection, image generation, and graph node classification. The two new benchmarks are highlighted in blue and bold. So for the LLM model pre-training, we had Llama 3.1405b, but that's obviously a very large model. So we've added Llama 3.18b, which is much smaller. We'll go into more details. It's trained on the same data set, the colossal crawled clean corpus C4. But it has a bit of a tighter quality target so that we can get a long enough training time to be substantive for the much smaller model. Then for image generation, we have Flux.1, which is run on a text-to-image generation data set. And we'll also talk a bit more about the validation loss criteria we have when we discuss that benchmark. Yeah, next slide. Great. So going into more detail on Llama 3.18b, this is specifically replacing BERT, which we had prior. So the BERT benchmark is now deprecated. The reasoning being that BERT is an encoder-only model. It feeds in the tokens, and you want to get classification out of the text. So it's more like a natural language understanding model. But we wanted to switch to modernize the architecture. So Llama 3.18b, this is a very modern decoder-only LLM, very standard transformer architecture. Also, it's small enough that it can be run in a single node, up to 8 accelerators. So we wanted, this is something that's, 405B. It's takes a lot of GPUs to train that one effectively, but this is going to be a much smaller form factor, which is easier to train. Other things here is that rolling out 3.18b, this is matching the rapid adoption of and capability of small models. So other examples are like Llama 4 Scout, Qwen 7b, Gemma 12b. So models in this form factor of around 10 billion parameters are very interesting, and we wanted to have a benchmark that reflects that area. This is also a low enough parameter count that it will fit on a small number of accelerators, ideally less than or equal to 8, which is be like a single node, or a single rack of common accelerators. And this is still a very popular model with there's more than 1 billion Llama downloads. So Llama 3.18b is very popular. Next slide, please. All right, and this is a more detailed comparison. Let's see. So things are pretty much the same. It's from the same herd of models as released in the paper as 405b. But you can see that there's a fewer number of layers. So from 126 to 32. We have the model dimensions are smaller, so that means there's smaller matrices. There's fewer and there's smaller matrix multiplications. Although we have a larger vocabulary size with 8b versus 405b, so there's some more expressive power as well with these models. Big change is the difference in starting point. So with 405b, we started from a checkpoint and we trained forward from that. And then for Llama 3.18b, we switched to random weights. Two reasons for this. Main reason is it's easier for submitters. They can work from kind of like any random checkpoint and start training. And two, this also, since it's a smaller model, we can train it. We don't have to start from a specific checkpoint to get ahead. With 405b, the model is so large, starting from a checkpoint, it also helps us set a different convergence target. All right, next slide, please. Cool. And now Flex Point 1, to go into more detail on this benchmark. So this is replacing Stable Diffusion v2. Again, the idea here was we wanted to match the image generation quality of these modern models like ImageN 3 and Stable Diffusion 3.5. The big difference between this one and Stable Diffusion v2 is again, the architecture changed. It's become kind of like it's a more streamlined transformer. So Stable Diffusion v2 is based on the UNet architecture. So it's this kind of pyramidal convolutional network where you have to squeeze the image and then expand it back. Whereas Flex Point 1 is a modern transformer style decoder only. Well, it's not a decoder actually, but it's just a modern transformer architecture with attention. And it also has, some of the getting the larger parameter count sizes where like Stable Diffusion v2 is less than 900 million parameters. It also is still an open source architecture, which is one of the requirements for being put into the MLPerf training set. And we have some more details on the next slide. And so this shows the diffusion transformer blocks that FlexPoint 1 is built around. So there's variational encoders at the front and the back, but in the core, we just have a bunch of transformer block layers. So this shows kind of how specialized architectures, as we go forward, we're seeing just kind of generalized transformers with a few changes are very expressive, very powerful models. So the change to this benchmark reflects that trend in the industry where just the rising popularity of transformers. It's also when you have a lot of the same sizes of the matrices and the same sizes of the blocks, it's easier to program against, easier to optimize sometimes. The reference implementation is built with Meta's Torch Titan, which is another open source framework. A couple other changes that we made, instead of using expensive validation metrics like FID and CLIP, we're actually using just validation loss, which is much easier to score. You don't have to score it against a corpus of images. You can kind of just look at and score images independently. All right, and next slide, please. Great. Now I can hand it off to Shreya, who's going to continue talking about some of the exciting results in V5.1.
Thanks, Paul. Hey, everyone. Let me talk a little bit about the results. Next slide, please, Laurie. All right, so the first thing I want to talk about is the submissions that we got itself. So we got like more than 180 submissions in total this round. And to compare to the previous rounds, let me just paint a bit of a picture. So we're currently at round V5.1. That's in 2025, sort of November. 5.0 was about 6 months ago. So that was in May this year. And then 4.0 and 4.1 were both 2024. So 4.0 was early in the year, so around May, and 4.1 was about a year ago. So about October, November last year. So if you want to look at the trends in the number of submissions over time, we see about a 20% increase in the total number of submissions from like 4.1, which was exactly about a year ago. So we see that there's a lot more adoption. And specifically, if you're looking at benchmarks like Llama 270B, LoRa, and RGAT, these two were introduced for the very first time 4 rounds ago, so in 4.0 last year. And from then to now, you will see specifically the RGAT plots and the Llama 270B plots. So you go from few submissions in blues going up to like yellow and green, which are this year, green being 5.1, where we see a lot more submissions. So we've seen about 1.8x and 2.5x increase in the total number of submissions for these two benchmarks, RGAT and Llama 270B LoRa. So we do see that for benchmarks that we added in the last 2 years, we're seeing a lot more adoption. Next slide. Right. And specifically, if you look at the last 4 parts in this bar chart, those are our Gen AI benchmarks. So the generative AI benchmarks that we're talking about is Llama 270B LoRa, Llama 3.1405B, and Llama 3.18B. And then we have Flux. So for these four, specifically, we see that there's been a very good increase, or there's a lot of adoption. So if you just compare the Llama 270B LoRa, which is our fine-tuning benchmark, compared to just last round, we see about 20% more number of submissions. And for the Llama 3.18B, which is a benchmark that we just added that Paul spoke about, we saw the second highest number of submissions, so 39 submissions this time. And that's actually very, very high compared to all the times before, especially for a new benchmark. Just, yeah. So next slide, please. All right, so speaking more about momentum around the Gen AI benchmarks, in 4.0, that was last year, the total number of submissions that we had on Gen AI benchmarks versus non-Gen AI benchmarks look like the plots here before. So the blue line right in the beginning with 135, that's the number of non-Gen AI benchmarks. And then the number of Gen AI benchmarks was a lot lesser. But as we go ahead with the number of rounds, we're seeing sort of like a flip in this where a lot more submissions are on the Gen AI benchmarks, and the number of submissions that we've got on the non-Gen AI benchmarks are lesser. And I think that's very representative of the trend in the industry right now as well. So this is what this specific plot shows us. Next slide, please. Right. And if we talk about the specific performance improvements this round, I'd like to talk about the 8 processor systems. So what we've done here is compared the scores on 8 processors for benchmarks that fit on 8 processors, and we've compared them over time. And in this, you can see that if you look at 4.1, so that's about 1 year ago, in general, we've seen somewhere between 1.5x to 3.9x increase in performance. And for the Llama 270B LoRa benchmark, that's the one where we saw about 80% increase in performance in 5.0 itself. And yeah, here the 8 processors is 8 accelerators. So that's what this basically tells us. Next slide, please. Now, this plot actually talks about best performance across all scales. So we're not restricting to just 8 processors or like a small system, but this is just the best score that we've got for each of these benchmarks right now and historically. If we look at this specifically, we see that the scores are either getting better. So smaller is better. So they're either getting better or they're sort of saying the same. For some of the older benchmarks, we're not seeing a lot of improvement, mostly because they've already been optimized a lot. But for the newer benchmarks, those are the last few ones, we see about like a 40% increase in the Llama 270B LoRa performance when compared to the previous round. And we see pretty much a 2x increase in performance. So basically about half the amount of time to train for the Llama 3.1405B, again, when compared to the previous round when it was introduced. So that's what our performance improvements look like this time. Unfortunately, we don't have anything to compare for the 3.18B and Flux, but we'll have those numbers in the future for future rounds. Next slide, please. What all of this basically tells us, right, is the first thing we should probably look at is what is driving these performance gains this time. And our analysis and assumption is that it's the new processors. So we have 5 new accelerators and 4 new host processors. Also, all the submitters are optimizing and scaling their Gen AI workloads. And now we have 4 out of our 7 benchmarks in the suite are Gen AI workloads. So we see a lot more performance gains on these Gen AI workloads. Additionally, there are a lot of software optimizations and algorithmic techniques and very advanced networking. And that's what is driving our performance. How we're keeping pace with the industry is essentially we have replaced both BERT and Stable Diffusion, which were a bit dated, with Llama 3.18B and Flux.1, which are newer models, have better quality, and are also architecturally more representative of what's being done right now. And the suite in general has benchmarks that represent all the key tasks. So if you're just thinking about like LLM space, then there's pre-training, we've got fine-tuning, we've got text-to-image generation. Additionally, we have benchmarks covering recommendation, graph neural networks, and vision applications. So given this diverse field, we're still able to keep a good pace with the industry. So yeah, next slide, please. Right. When you go over the results, I'd just like to say that every result says something interesting. And a lot of work goes into every result. Training is extremely hard to do. And each of these results are really hard to get. So always look at that first. And when you're trying to compare a bunch of results, I'd say look at submissions and look at the ones that are similar across dimensions like vendor or scale or performance, and then different in just one of the dimensions. And that's a good way to compare them when you're going over the spreadsheet. Some more things to note is to look at things like scaling over time, the way we just spoke about some of the insights. So it just helps putting time into perspective, and looking at software tuning that happened over time. Additionally, some things to note is the new software stack and the new processors that have been introduced this round. And yeah, very importantly, there are a lot of different networking that has been done, especially for the multi-node submissions. Our supplementals have details from each of the organizations explaining their setups really well. So I think that would be really good to understand our results as well. Yeah, next slide. Right, I think that's the end. So questions?